thank you very much, and thanks for the invitation to address this august audience. So, as Alan said, I joined the association earlier this year, so I consider myself a novice when it comes to airships, but this was a great opportunity to come and present some of my research, and particularly our interest in using airships potentially in some of the research we're doing. So, I'm Christine Gommeginger, so not Professor Christine, just Christine is fine. At the National Oceanography Centre, which is based in Southampton and in Liverpool, as I will explain in a moment. Come up from Southampton this morning. So, the talk, as you can see, has got a very grand title around early warning system for climate tipping points in the North Atlantic, and the use of airships and other airborne platforms to help us in this respect. So can I just have a quick show of hands of how many people are familiar with the idea of climate tipping points? Okay, that's great. I won't have to explain it, or well, I'll explain it briefly. So this is actually a first as well, because I've never done an after dinner speech or after lunch speech. But what I'm told is you have to have jokes. So I scratched my head and thought, right, what joke is appropriate for an audience who do not know is always a little challenging. So I scoured the internet for jokes about airships, and there's some really bad ones.
We know.
So I come up with this one. What's the difference between a good after-dinner speech and an airship? Does anybody know this one? Any suggestions? Okay. One is full of hot air, the other requires a license. Anyway, so best I could find. So you'll be the judge of how much hot air there is in my speech and whether or not they need a license. Anyway. Okay, so this is what I'm going to talk about today. So I said it'd be a little bit about myself and the National Oceanography Centre. And then I'll introduce really the bulk of this, which is around this issue of climate tipping points and its relationship with global ocean circulation. And then, to everybody's disappointment, probably, I'm going to talk about the Aerostats project. So we're not talking about aerostats, but the Aerostats project, which stands for Aerial Experimental Remote Sensing of Ocean Salinity, Heat, Advection, and Thermal Headline Shifts. Because that actually spells out aerostats, indeed. And I won't be tempted to quiz you on knowing what aerostats stands for in future.
Yeah.
And then I will say a few words about our plans for an airborne campaign in Greenland in a couple of years from now, hopefully, and particularly outline some of the needs and the challenges, and give you some conclusions, final remarks, and then open to you for questions or indeed comments. So make sure you have lots of questions and comments. So a few words about me and National Oceanography Centre, that's me. So for those who haven't spotted, I have a slight accent. So this comes from France. I did my studies down in the south of France, University of Toulon-Nice in remote sensing, telecom, that sort of thing. And then in 1997 I came over to the UK, never to look back. Came over as a Marie Curie fellow and basically never left. So I'm now a principal scientist in satellite oceanography. That's my background, really. Also a professorial fellow at the University of Southampton. And my specialism is in ocean remote sensing. So it's observing the ocean primarily from satellites, but increasingly also looking at other types of platforms. So it's really my particular interest in developing new ways of observing the ocean remotely by looking at new instruments and now also new platforms to do what we need to do. And for those who haven't heard about the National Oceanography Centre, it's one of the largest centres for marine research in the world. And in the UK, we are based both in Southampton but also in Liverpool. And we do a very wide range of research, science, technology, climate modelling type things. We've been going on for quite a long time. We're now an independent charity, company limited by guarantee, with charitable status, for a few years, and we have lots of staff, lots of students. So just to give you a flavour of the sort of research environment that we operate in. And the remote sensing side of this is a small, but obviously very important component of that. So global ocean circulation and climate tipping points. So I'm sure many of you would have seen this figure. This is the sort of conveyor belt, the global thermohaline circulation. It's really the most important aspect of the ocean in the climate system, is its role in redistributing heat and nutrients and all sorts of other things, fresh water, also salt, if you want to think about it, around the world. This type of conveyor belt is really driven by differences in density between different water masses. So, changes in temperature, differences in salinity. And what's really important to know is that this conveyor belt is really kind of powered by a couple of sites in the world where you have this sort of deep water formation or ocean convection. And there's one in this area here, in the North Atlantic, and the other one in the Southern Ocean. So these are really key areas in the global ocean where there are changes happening, which are potentially changing how the ocean is circulating globally. So if we just focus on this North Atlantic bit, this is sort of a more detailed view of what's going on. And on the current warming that is happening due to climate change, we know that there are massive changes to Greenland's ice sheet. So I believe Greenland is primarily covered in ice, and that ice is melting very fast. And one of the big questions we have at the moment is what happens to the fresh water that's coming off Greenland. It goes obviously into the coast, but then we don't really know what happens to it. So you have all these really complicated currents, cold currents coming from the Arctic here along the coast. And we've got warm currents coming up from the Caribbean. And the North Atlantic, that's this subpolar gyre, this kind of recirculation of some of it and some mixing going on. So this area here is particularly important because that's where the changes in density of the water is happening. And then we have this huge influx of fresh water happening at the same time. And of course, fresh water, much lighter than salt water, so it really could impact the density very strongly. And so this is one of the climate tipping points that's been identified. And the tipping point is when the system is kind of gently pushed out of its normal equilibrium and potentially could tip very, very rapidly in a completely different mode. So this is a satellite image of sea surface temperature just off the coast of Greenland, and that really illustrates very clearly what I just said around this sort of cold current coming down. You see this temperature difference, so temperature go from like below zero around the coast to something like balmy 12 degrees offshore. And so you've got this really cold water coming here, some of the water coming off the fjords, etc. And what we see from this satellite image, which is a resolution around 1 kilometer, is that we see a lot of very complicated things happening here at this boundary. And we know that there is some of that cold water is going into the Atlantic, but we don't currently observe that. And the other thing about this is a thermal infrared image, which of course cannot see through the clouds. So all of this here are clouds, which is a big issue for satellites, particularly in this area. We can do the same with optical sensors. So this is again an image from a satellite in the optical visible spectral bands off the coast of Greenland, slightly different time of year. This was in June. And what you can see again, so first of all, you can also see marks of sea ice. So this is actually residual sea ice, kind of winding its way around the tip of Greenland. And you can see how that is modified by currents and so on through those meanders and so on. And in fact, in this case, you can also see these incredible patterns here further offshore. These are actually algae blooms. This is in June, so very strong algae blooms. And again, you can see these incredible patterns, which are fingerprints of the currents in this area. The reason we care about this type of thing is that these are also fingerprints of vertical transport of water. So by understanding what's happening in the horizontal, we understand how much is also being vertical, which is all this idea, again, about convection. Okay, so for how do we deal with this in a sort of forecasting tipping point context is we use models, climate models, ocean models. And this is really to illustrate the sort of different types of spatial resolution that we have in our climate models. So when you talk about climate modeling, the ones that we use for Paris Agreement and all these kind of things, they are usually at this type of resolution, so 100 kilometers. So as you can see, the figure is very blurry, and you can just about see the main dominant kind of current systems. Quarter of a degree is more typical, and then really where we're looking at now is sort of 1/12 of a degree, so about 7 kilometer resolution. And as I showed from the satellite image, we know that these sort of small scale processes actually really matter. So one of the uncertainty we have at the moment is that if you use these different models at different resolution, they give you different answers to forecast tipping points. Around half of the models say it will definitely happen, and half the models say it will definitely not happen. Which is not correct at 50-50, but if it does happen, it will have major consequences. So this is an example where it does happen. So this is one of the highest resolution models that we're running at the NEC, in fact. And what we're seeing is you have this sort of time axis here, into the end of the century, essentially. And what this is showing the how deep the surface water mixes into the ocean. And so the redder it is, the deeper it goes. And what we see is from here, from this model simulation, is that we have this sort of normal pattern of cold water, deep water formation, and so on in weeks, etc., etc. And then very rapidly, around 2040, we have an abrupt cessation. This is a typical tipping point behavior. Where all of a sudden, you have a system that sort of tips and convection stops. And from then on, there is no longer any deep water formation. This is quite a problem if you're interested in, for example, fisheries, because ocean convection also brings up nutrients to the surface, which is needed for phytoplankton and fish, etc. So if this happens, this is like the end of fisheries in North Atlantic. Obviously quite a big deal. But like I said, 50-50 chance at the moment, so this may not happen, but it would be good to have a bit more certainty on that. So this is where our project comes in. Oh no, we just do a little bit of that problem, aerostats. So, as I said, we have models, and we have some observations, but not necessarily the observations we need to understand this exchange of fresh water and heat between the Greenland ice sheet and the Atlantic. So what we're doing, so airships, this is what we're doing in the first instance. We are looking at different types of airborne platforms, and the whole story around airships started really with the Airlander story a few years ago. They kind of had a huge, I know there's somebody from the hybrid air vehicle here. This is really where we started to think, oh, this sounds interesting, perhaps we should have a look at that. So this is why we have Airlander picture there, but we're looking at all sorts of airships. We're also looking at HAPS, so stratospheric platforms, high altitude pseudo-satellites, and we're also looking at drones. We're also doing some other things, like we're developing a new sensor to do currents, and we also want to do this really crazy thing, which is to do year-round observations of ocean color, temperature, and salinity, which is, I'm not going to talk too much about that today. So we're in the first phase of this project. Sorry, I meant to say, this is happening in the context of ARIA, which stands for Advanced Research and Invention Agency. This was a new funding agency that was set up a few years ago. It was actually set up under the Boris Johnson's government. And it's really aiming at funding high-risk research, which would not get funded any other way. And they're throwing a huge amount of money at issues such as forecasting tipping points. So in this particular instance, it's in context of this, but there's many other programs as well, including one with new airborne platforms, which is launching very soon. So it may be of interest to some people in this movement. Anyway, coming back to aerostats, so we started in April this year, although it feels like we started years ago. And we have essentially a couple of years to do all this thing, like looking at airborne platforms and all the other stuff. And if our funders like what we propose, they will fund us to do a campaign in Greenland, where we have an airborne campaign to do, all the fancy stuff like demonstrating capability all year round and so on, with also some deployment of autonomous underwater vehicles. And then finally, we kind of put it all together, validation and so data model integration. This is where it all comes together to really use these new observations to test the different models to give some improved certainty around which of these models could be trusted for predicting tipping points. So it's quite a long project, 5 years, if it goes to completion. At the same time, it's very short, because we're looking at the campaign in this sort of time scale. So 27, 28, actually very soon. Some things will take time. It's not always just money. So the Greenland Airborne campaign, if we manage to get there. So some of the requirements and challenges. So this picture shows Greenland and the main airports in Greenland. So assuming we have an airborne platform like a drone or something that needs a runway, these are the only kind of main airports with runways in Greenland. And the little circles kind of show the 200 and 500 kilometer radius from it. Now, our areas of interest are going to be at least 200 kilometers from those airports, and in some cases even further. So the first requirement for platforms is endurance, because our targets are quite a long way. So we're looking at range capability of 800 kilometers or more, flight times at least 8 hours, and of course beyond line-of-sight operations. That already takes out quite a few of the smaller drones, for example, are really not going to be suitable for this. The second thing is flying over the ocean is not for the faint-hearted, particularly in this area of the Atlantic. The Atlantic is actually the area of the ocean with the highest waves in the world. Everybody thinks the Southern Ocean is really wild, but actually North Atlantic is worse. Has much higher waves in the North Atlantic, simply because of the type of storms that we have on the constricted basins. So this is, for those who have spotted this, so we have quite high winds. This is a satellite measurement of winds, what's known as a tip jet, so very, very high winds in this area. And for those who wonder, this is 50 meters per second. So that's 100 knots. And the other thing is, of course, icing, which is a really big issue for anything airborne. And it's not one or the other, it's both, obviously. So, payload capacity. We have instruments which are going to be of the order of like 7 kilograms each. And we do need to have a platform that can accommodate those, both in terms of mass, but also volume. And of course power, although our power requirements are not that huge. But for some platform, that's a real limitation. Nominal altitude, we're looking at like 3,000 meters. Where it's not a very strong requirements, but 3,000 meters would be good. Except when you want to fly under the clouds. That's the next bit. That's a photograph from our recent trips to Greenland, taken at midday in October. You can see clouds can be really quite low. Those icebergs are big, but not that big. And really just to illustrate that we have a lot of clouds in this area. But even when it's not particularly cloudy, the light levels are not great. So it really is probably one of the worst places in the world to try to do this. But this is also where we need it, because we have hardly any observations in this region. One reason we want to do airborne rather than satellite, we want to take several measurements in the same place per day, because some of these phenomena are changing very rapidly within a day, and the satellites will not allow us to do this. Satellites cannot see through clouds for the optical infrared, and they cannot do the sub-daily sampling. So once you start to think about this, the logistics involved in that, we are also increasingly worried around the accessibility and the remoteness of some of these. You know, the airports that I mentioned, they are really only accessible in summer. In winter, if you want to have have some cargo you want to put in there, you can only do that by ship, and you can only do this when there is no sea ice. And that means you can't do it in winter. So the remoteness and the difficulty in actually doing fieldwork in this area is considerable. And so we are very much looking at options that give us autonomous operation, also remote operations, which again is a real demanding requirement for some of these platforms. So I don't know how I'm doing for time, but I think I'm coming to the end already. So this is the current status, sort of a very easy green, red, sort of, what is it, green, amber, red, whatever. For the different types of platforms, I've divided the drones into what we call category 1, which are the ones anybody can fly without a license or within line of sight, or category 3, which are essentially autonomous aircraft, much bigger wingspan, much bigger payload capability, cargo drones essentially. And so we have different requirements there. So airships are faring relatively well. There's just, the main issue we have at the moment is the access to an airship and the unknown around the cost. Because in other respects, it's faring really well. Year-round observing, capacity for payload, endurance is great. Okay, high winds and icing is an issue, but it's an issue for essentially anything that operates in the troposphere. The HAPs are doing well for that because they are outside the weather. So the HAPs are doing well on that. But their payload capacity is rubbish at the moment. And the ones that rely on solar power are not good for a year-round observing requirement. The drones, well, the small drones are doing really well from the accessibility cost because they're quite cheap. Actually, some of them give you this sort of remote operation, but they are faring very badly on endurance, high winds, capacity for payloads, typically 1 or 2 kilograms. That's not good for us. Year-round observing depends really how courageous they are to fly in high winds, for example. So our two front runners at the moment really are the large drones and potentially the airship, except for that last bit. And I'm hoping that somebody's going to stand up and say, I got one! All right, it's no problem. And it's very, very good rate. So that's it. Final remarks. High-resolution ocean data are needed to sharpen our climate models and clarify the North Atlantic tipping point risks. This is actually quite urgent. Our project Aerostats is exploring affordable, low-carbon airborne ocean sensing using airships, HAPs, or drones. And if we are funded, we will be able to fly our first Greenland airborne campaign as soon as mid-27, 28. And that in itself is one of our most stringent requirements, is that the timescale for this is relatively short. That's it. Thank you very much. I don't know if anybody's thought of any questions.
Yeah, I
Yes,
have a
please.
question about budgets.
Yeah.
Clearly, whilst you're a charitable organisation, platform owners and operators in any of the categories you've mentioned won't want to give you their platforms for nothing. So is it correct to assume that you have a substantive budget in your programme to cover the costs of the platform, whichever it may be?
Define substantive, but yes, we have a budget for the phase 2 to actually implement.
I mean, more than a DJI Hydra.
More than that.
Right,
yes.
okay, good.
Sufficient to cover some eventualities. Sufficient to be worth considering, definitely. So yeah, there is a budget there. And literally, this first phase is to review our options. And then at the end of that, or sometime next year, we will be putting together a plan that we put to our funders and say, this is what we want to do, and this is how much it will cost. And then they'll go and decide whether or not they wish to do it. This is the situation we're in.
I'd like to actually kick off a proposal that at our next council meeting, we consider offering the collective knowledge of the Airship Association to assist you in identifying suitable airship platforms formally.
Okay.
Obviously, we need a council decision to do that, but I think it would be the sort of thing that the Airship Association could readily contribute to your programme.
Thank you. Sorry, just behind you first.
What was the cruise speed requirement for your platform?
We don't have any cruise speed requirements. I mean, drone type speed or airship, they're all suitable. It's not a discriminating factor. We can work with all of them. The question is more linked to endurance.
Well, yeah.
Your speed determines your how far you can go, your endurance.
Your range.
Your range, yeah. So it's more in that sense than any other. But from the instrument point of view, we don't have requirement on cruise speed.
Okay, because obviously you need to contend with the winds.
Exactly,
If
yes.
cruise speed is too low, then
Yes.
you might not get where you want to get.
That's right. So if you have good endurance, then it doesn't matter, it just takes longer to get there,
Yeah,
which is not such an issue for us if you can stay there for long enough to take your measurements. That's fine. But obviously, if your endurance is not sufficient and it jeopardizes the platform viability, then that is another question.
We could always just fly backwards.
Yes?
That was leading on to my question, which was whether you have any more detailed data on wind speeds. Those are scary in the area.
Yes. Yes,
Do you have any laminar by altitude and by season as important than this?
we are doing that as well, yeah. But we using primarily models, so reanalysis data and stuff like that. Unfortunately, going higher does not help. It tends to get worse, right, as we get higher. Getting very close to the sea surface is also an issue because of the icebergs and the icy states. So, it's a very, very challenging environment to operate in.
Interesting.
I mean, it's not always 100 knots, right? So this is a particular extreme example of what is known as a tip jet. But those tip jets, again, are really interesting scientifically because they are the strength of the wind determines how much heat is extracted from the ocean.
Yeah.
And if you extract heat from the ocean, the water gets colder and it sinks. So it links again to the ocean convection issue.
Have those historically been predictable?
Very poorly predicted. Extremes are generally poorly predicted. It's also relatively, even though the impact looks big, the generation area is very small, and that area is not necessarily very well captured by the models, atmospheric models.
Yeah. The trouble is when you lead in unreliable or difficult to record data into your models, you end up with unreliable models.
Yeah, we do need platforms who have got some resilience to uncertainties and things like weather. The more robust, the better, really.
Yeah.
But without being too costly.
So,
Yes,
a logical question from that, then following on from my earlier question. Have you considered tethered aerostats? Is that something you dismiss till the conditions you settle on that?
I think there's some. So we have So we've dismissed the idea of balloons because they just would drift out of the area very fast. And the idea of tethering to that type of altitude, to 3,000 meters or so, in such high winds, introduces all kinds of difficulties. First of all, the strength of that tether, and also the fact that you'll be measuring not at that height first. It's quite hard to keep it vertical. So we kind of discarded that solution. But thanks. Yes.
Yeah. How wedded are you to the 3 kilometre altitude figure? So I'm thinking push up into the lower stratosphere and you've got a much more stable air mass.
Yeah.
Is that viable for your observations, or do you need to be lower down?
So for one of the payloads is a microwave sensor. So for that, it would be fine.
Yeah.
You could go higher. I mean, you have implications about power budgets and things, but that is something we could live with. The 3 kilometers is really it's this issue of pressurized cabin or not. I mean, it's historically you have used aircraft, manned aircrafts for this type of thing. So that is the altitude we typically operate at. We don't mind going higher, but at the moment we have an issue with the stratospheric platforms that we have come across, which have very limited payload capability and would not be able to give us either the mass or the power requirements that we need from those higher platforms. But yes, in principle, we'd love to go higher for that particular platform. We're not wedded to the idea of putting everything on the same platform, so we could have, a smaller range for some of the other sensors to go below the clouds and have something higher, stratospheric platform for this new instrument that we're building. That's a possibility. Sorry, there's just somebody waiting at the back. Yes?
Oh, sorry. In your modelling, and forgive me if you covered this in there, you mentioned that 50% of the model said it wasn't going to be horrible, and 50% said it was going to be okay.
Yeah.
And the model seemed to run on different resolutions.
Yeah.
Was it the high resolution ones predicting doom and gloom?
Yeah.
Was that the split?
That's the worry, yes. It's the one that are more realistic that actually predicting a tipping point for ocean convection shutdown. That is a concern.
Yeah.
Is that if those models are correct, it could be getting really catastrophically bad quite soon. The large majority of climate models do operate at 1 degree, the 100 kilometer resolution, and by and large they do not. But at the same time, there are many, many aspects of the world, of the environment they're not getting right either. So there's a concern that the bad news may be closer to the truth, unfortunately, which is often the case.
Yeah. Thank you.
Okay. Sorry, this gentleman over here.
2 things. You showed the red and green boxes,
Yes.
and you showed airships having a grey box for high speed, wind and icing.
Yeah.
We had a paper given at one of our conferences by Norman Mayer, who reminded everybody of an American test in 1954 called Operation Whole Gale.
Mm-hmm.
And in one of the worst winters in the North Atlantic, 1954, the US government gave their airship stations and their fixed-wing stations an area of the North Atlantic to patrol. And in one of the worst winters, the airships were on station 10 times longer than the fixed-wing. And they proved that icing was not a problem. And the thing is that the US Navy's blimps have been forgotten because they were military secrets.
Mm-hmm.
A lot of their achievements, they flew at 70 knots.
Mm-hmm.
They had a crew of 25 people and they could stay at sea for a week.
Yeah.
So I think that box ought to be green.
The reason it's grey is there are also smaller airships which would not be able to do this. So this is a very simplistic way. Remember, in each category, there's going to be a multitude of models, right? So Kilo, for example, is an
Well,
airship.
your red box means that you can't go and get an American blimp from the Second World War, right?
Yes.
Secondly, aerostats. I was part of a project that was triggered by the Exxon Valdez crisis when thousands of tons of oil was spilled in ballistics. And the oil companies got together and said, if this happens in the North Sea, we're in trouble.
Mm-hmm.
And they founded this organization called NOFO, which is the Norsk Oil something or other. And we installed small tethered aerostats in containers that could be put onto the decks of ships.
Right.
So all the ships that are servicing the oil rigs, if there was a big oil spill, they would go and pick these containers up, and they could put up a balloon with a camera, because the problem they've got these booms that scoop the oil up, but the captains of the ships can't see where the oil is. With a camera, they can see it like that. So those systems are very small balloons, but the point is that if you had a ship with a hangar on it built in containers, you could put a very big aerostat, and I mean, skills tell me TCOM fly there 71 meters in very high winds to very high altitudes. So you could go and get that off the shelf.
Yeah, so we haven't, there's a couple of things. One is we are avoiding the use of ships, because ships themselves are extremely expensive. I assume, because you have they are manned ships, right? The second thing is that this area of the Atlantic is, in winter, is essentially avoided by all ships, but the weather is just so extreme. So we have also thought around deploying platforms for the ship, perhaps, but that is the bottleneck, is that we need the ship, and we try not to have a ship, essentially. So, thank you. In North Sea, I think you're right, because that is more sheltered, there's more activity, human activity in any case. So that's more likely, but North Atlantic is particularly tricky.
Perhaps you could deploy it from an iceberg.
Just one there first, and that's up to you.
Yeah, I was going to say what you're saying about the circulation stopping of Greenland. That's all part of the Atlantic, like, the jet streams are called, or stuff that comes up.
The Atlantic circulation, yeah.
So if that slows down, does that mean less hot? Does that mean lower temperatures in Europe? Right?
Yeah.
It'll blow.
Yeah.
There'll be less hot water coming from the Caribbean.
That's right, yeah.
How
Essentially,
strong is that?
as you know, the Western European climate is considerably milder than the North American climate. And essentially, this is partly one reason for the milder climate in Europe, is because of the effect of the ocean bringing up all this hot, warm water from the Caribbean to higher latitudes. So if that slows down, indeed, we are looking at a much colder climate over Europe. So the impacts of this will be considerable, both locally in the Atlantic because of the convection changes and, like I mentioned, the fisheries, but also in terms of weather over Europe. Yeah. I know it's doom and gloom, and I'm sorry.
We've got the solution for it.
Climate change is not a happy science, I'm afraid. Sorry, there was one more there.
Yeah, so you just talked about operations in winter. So what is the anticipated season, or which month in the year are you planning to do such operations?
So we want to demonstrate it year round, which doesn't mean we want to be there continuously all year, but we want to be able to demonstrate it in different seasons. So ideally we start in summer, and then we gradually increase the bar by going in autumn, spring and winter. That's why it's a campaign over like 18 months, so that we can select the different seasons. So the idea is really to do a campaign of a couple of weeks in different seasons, but to do them in every season. At the moment, the observations we have in this area are mainly summer data. So we have no idea what's happening the rest of the year. And a lot of these phenomena of convection are happening in spring and in winter and spring.
Just very briefly, I'd like to thank my colleague Giles for turning one grey box to green. I'm going to turn the other grey box to green for airships, because there are plenty of examples of remotely piloted and autonomous airships ranging from small models to much bigger airships that are being thought about and contemplated at the moment. So I think we end up, as the Airship Association, with 1, 2, 3, 4, 5 green and 1 red, and I'd argue that the red can possibly be turned green as well if we connect it with the right people. So, thank you.
I'm delighted to hear it. Sorry, there was other, yes.
It seems to me least likely that the USA, Canada, and maybe Greenland itself are interested in just such observations. So what scope have you for international cooperation with similar bodies?
It's a little difficult interacting with the US with anything linked to climate right now. Yes. Canada is much more open to this type of initiatives, and they do have programs, I think, to do with using airships, particularly for cargo, into high latitude, because they have issues around, the remoteness of the high latitude Arctic. So the Arctic is becoming an area of intense interest. And so anything that can provide connectivity to those remote areas is going to be welcome. So Canada is looking into airships, I know. Although, again, it's very much from a more cargo type thing rather than research. Sorry, it's taking too long.
One final question.
My question's actually already been asked. I was going to ask about autonomous and remote because I had the same thought that,
Okay.
that that's very solvable. But,
Okay, I wasn't aware that there were autonomous airships, so
And send you some information.
apart from the Hindu one, but that's too small.
If you do it on paper.
Okay, thank you very much.
Thank you.